and work it out. Okay, so on my screen, it has different things on Moodle, so maybe refresh it. I don't know.
All right.
It like, I only have one thing. Can anybody else see that?
Yeah, that's really weird.
Yeah.
That was my bad. I went into the Stats 2 class from spring 2017.
Oh, okay. That makes sense.
Yeah.
Okay.
Sorry, Jordan.
No, it's fine. Yeah, so we're going to do correlation and regression today. Yeah. So, what is a correlation? And what is the difference between a correlation and a regression, right? So, we, like, you know, in undergrad and stuff, you talk about correlations a lot, and I think a lot of people, like, misunderstand kind of what it is. But it's basically just talking about how much, you know, you can use different words, how much are these things related, how much are they associated with one another, that type of thing. And it's not talking about, like, causation, of course. Correlation does not equal causation. Not predicting what's going to happen in another variable. It's just, like, how much are they related. And it tells us the magnitude and direction of that association. So if one thing goes up, does the other variable go up with it? Opposite, if one thing goes up, does the other variable go down? So that's talking about the positive association, negative association. Yeah. And, you know, there's differing determinations of, like, the size of the relationship, but we'll just go through by this one. So small is under 0.35. Medium, and then large. If you have, like, strong opinions about what these determinations should be, that's fine. Just, like, make a good argument for it, because I believe it. There's a lot of different literature on it. So, yeah. So basically, we can just go through running it in SPSS. So you can open dataset 1. And so what we're looking at here for the example is, so we're talking about relationship between depression scores and income. And then also in this data set, it separates it out into different Asian American groups. But I think for the first part we will, oops, that's not that right. Okay, so it's data set 2, not 1. Okay, so we have a couple new assumptions that we're going to talk about. So, you know, we have our regular univariate normality. And we do that through the chaos test, the histograms, the plots, all that crap, which, you know, is our favorite thing to do ever. But then we're also adding bivariate normality, and so that's talking about how do the two variables relate to one another, basically. Like, is their relation to one another normal in the population? And so we're going to use a plot to do that. Yeah.
The bivariate normality differs from univariate with the scatter plot.
Mm-hmm. Yeah.
What was your question? I said the bivariate normality is different from univariate normality because of the scatter plot.
Oh, okay.
Yeah.
And the answer is yes.
Mm-hmm.
But I don't know why.
Yeah, so I was trying to, let's go ahead and run the, because I think the bivariate normality comes out with the, like, when we do the regular stuff. So go to descriptive, explore, and we're going to put over income and ethnicity, or wait, income and depression. Yeah. And let's just do the whole group first, I guess. Doesn't really matter. So plots, histogram, normality plots with tests, because that's what will give you the KS test. So that's important. Otherwise, I think that's all we need. So let's run it. Cool. So, oh, okay. I answered my own question. So this is what we do for the univariate normality. For the next assumption, so bivariate and linearity, we make a different scatter plot, and we use both of them to answer this, kind of. So go to graphs, and scatter, legacy dialog, scatter dot, simple, and then we are going to click over, it doesn't really matter which one you put first, but just make, like, notice. So we're going to put income in X, and then depression in Y.
Wait, are we comparing subgroups?
For right now, let's just keep them together.
Okay, where did you go? You went graphs to where?
Graphs, and then legacy dialogues, and then
Which scatter plot?
simple.
Simple, okay.
Yeah, you can kind of mess around with it too, because there's different ones.
Oh, yeah.
Okay. So looking at this, I'm gonna have to double check on the bivariate normality, because that doesn't make sense to me using this, because it's like linearity and normality are different things, and it's asking you to like assess it in different ways. So I feel like that's a different plot, but I'll have to look up on that. But anyway, so it kind of is kind of along the line, but it's not really super defined. And so basically, like, when we write this up, you're just gonna make a determination about it and make a good argument, basically, because it's very subjective. Yeah. Okay. So then we have this other variable, or what is it called? Assumption, called homoscedasticity, which is like a really fun word. So we had the homogeneity of variance last semester, homogeneity of covariance, and now we have homoscedasticity, which is another thing. But basically that's talking about the homogeneity of error variance. So it's saying, does the variance between these two variables, is it consistent across all of the values? So it's saying, like this certain value of x, it's like consistent, basically. Like when you compare the two, it's not like there's like for x, it's like huge disparity, whereas other ones it's like really small. So that's all it's saying. And so then we also get a graph out of that. So you're gonna go to yeah, so you're going to go to Analyze, and then Regression, and then Linear.
And we have to remember which one we put.
Yeah.
So independent is the x-axis, and then dependent is the y.
Yes. Yeah, and so since it's like a correlation, it's like kind of either or, but it is important to remember which one you decide to use. And then there's a part where we have to, okay, yeah. So to get this plot, we are going to put, oh gosh, okay, it gets confusing. So the x is z pred. So we're going to put that in the x-axis, and then z resid in the y-axis. Cool? Okay.
Why?
Wait, what did you do?
Why do we know to do that?
So, good question. I don't know why it's like that. But also I'm following the instruction manual too. And so this is going to give us a linear regression for comparing these two distributions basically of the x and y axis, but really we're just kind of looking at these two different variables. But because it's a plot, we have to choose, the x and the y. Does that make sense?
Sorry, I don't know if it's in here somewhere, but I'll look it up. I don't know what any of this mean.
Me neither, to be honest.
Okay.
Yeah.
Do we have a manual like we did last semester?
Mhm.
We do. Oh. What was this?
For like this lab,
Like the SPSS manual that we had last semester?
like this thing, the packet.
No, the book.
Yeah, it's helpful.
Well, just because like last semester the book really like it was like a dumbing down of the process.
Yeah.
And it really helped me like.
I think Dr. Menon uses different books, right? And so you can always use that as a resource if you still have it.
We were done with it. There
There's
was another one that she
Oh,
has.
okay.
I can't remember what it's called, but she had a different one. Through Menon or through Menon? Okay.
So Menon probably assigned the field, or wait, is it the Howell or the field that
She was like
both?
Yeah.
yes.
Whichever one is like the simpler one, I really liked it. That's really helpful, and I have like all of this stuff in it. So if you want to use that as a resource, I have the book at home, but I don't use it, so I could bring it and like keep it on campus if you want that.
Did you not keep the survival guide?
What?
Did you not keep the survival guide?
No, I kept it, but it's finished. Like we edited it.
No. The survival guide has regression
That was
and
the other
correlation.
book that we got to the end of.
It doesn't
She
stop.
probably skipped around on the chapters,
Oh.
because like you could teach all of this in different orders, so I bet it just got skipped over. But it's
So
a
the
bit different.
survival guide does help.
Yeah, it basically covers all of SPSS's functionality.
Okay, so we're here. We put over those guys, and we're gonna look at it. So basically, looking at this going from left to right, it's pretty inconsistent, as you can see, and so you just kind of write about that. I feel like this one would not pass my test because it seems pretty inconsistent. So I would say, this assumption has been violated, basically. Because all that's saying is like at different values of x, this residual between the two scores is like not consistent across all of them. So it seems like there's like outliers kind of going on, something kind of weird with the data, and that it will affect the results that we get.
Are we analyzing this scatter plot, or do we analyze the one that we ran before? This is different because it's the residual.
Yeah. So we use, you can use the residual plot to assess linearity and homoscedasticity, but I think in my mind it's a little bit easier to like separate those two because it gets kind of confusing. And so using the scatter plot for linearity, I like doing that a little bit better, but that's just me because it's like, oh, you do this for that, and then you do this for that. But yeah, Homoscedasticity has a different plot, and this is the residual.
How do we interpret it?
So what we're looking at is going across left to right is the distance between, like, is it consistent? So up here it's really big, and over here it's very close together. So it's inconsistent.
And so what is this telling us?
So that's-
You just said it. It's inconsistent, but what does that mean?
Yeah, so that's saying that, okay, so for example, at like value of x, like 1, it's saying that the residual, the discrepancy between x and y values is like really high, whereas at value 2, maybe they're really close together. So it's like there's like a mismatch in the different values, because in a normal curve of scores, you would expect that it would be consistent across different values.
Okay, so if we have a bivariate distribution, it's not going to look like a normal distribution, right? But we would expect this to look normal? That's where I'm confused. What are we
Yeah.
expecting here versus when we just do a scatter plot?
Yeah, so this is a different type of plot than just like a regular scatter plot and the normality graphs that we were looking at. So before we had like, I think I'm throwing out some of the wrong like words when I'm trying to explain it. But so this is like our distribution of the scores based on frequency only. So for normality, that's what we're looking at there. And then for the QQ, like observed versus expected scores. Whereas a scatter plot, we are saying at this value, this score is, at this value of x, this is the score for y. So you're just plotting it on a scatter plot, right?
Yeah, I just don't know what I'm supposed to see on the scatter plot that's supposed to make sense to me. That's what
Yeah, okay, so going back to this graph, so this is our scatter plot for the linearity. What we're trying to see is if it's just like fits a line of best fit.
Right, but it's bivariate, it's not going to, right? That's where I'm lost.
Now I'm lost.
I think it is. It says here like let's see. The assumption is also assessed using a residual plot. The greater degree to it's basically saying that if you see a curve, that the assumption isn't being met. That's what it says.
But what, okay, let me try this a different way. What is whatever it is? Sorry, I can't understand.
Homoscedasticity.
Yeah, that
It's all
homo.
blurry on there. What does that tell me?
Yeah, okay, so do you understand the linearity part of it though, kind of?
I do, I'm still confused about bivariate versus.
Yeah.
It's just measuring the two variables together.
Yeah.
Are
okay.
you saying because it's by like
That's why I'm
modal?
confused
Is
about
that what it is?
Yeah.
There's two like
Um,
two peaks.
Okay. So next week I will clarify myself for the bivariate normality because I'm confused on that part. So just put that on the back of your mind. But for linearity, this is comparing, like plotting the values together on a graph. And we're trying to see if it resembles a line. So if it's super kind of wonky and curved, that's kind of showing us that it's not meeting that assumption.
So this looks like a line to me. Would you consider that a line or no?
Yeah, so that's what it's kind of subjective. So, like, it's kind of curved, like, it would probably, like, it's subjective, yeah. So, you can make the determination for that. I mean, I would say that it kind of does, but it's not very obvious, you know?
Well, it makes sense because the lower income
Yeah.
and the higher income, like those two like far ends of the spectrum are in line, but that one like section is lying off.
Yeah, yeah.
So
Yeah.
if it's subjective and like I were to argue that this was curve like, then I wouldn't do this regression.
No, you would still do it.
Oh.
So we have to separate out our assumptions that we're looking at, right?
Does this matter? I mean, obviously it matters that we have to write about
I
it,
mean,
but like in real life practice, does it matter?
that's a different conversation. Because this, yeah, you know, like that's
I'm just
Yeah.
wondering for me, like, is this just something I need to know to pass the test, or is it something that I need to know?
this is like theory, and so for like the prelim and stuff, like you should know this stuff. But okay, so there's like a differentiation between what happens in the field and the curriculum in like classes and
Right.
stuff. And so I can't answer that. It might be in your practice. Sometimes it might be relevant. Sometimes it might not.
Okay, let me ask you a different way.
Yeah.
Is there another way to test homoscedasticity? Is there another way, or is this the only way?
Probably.
To check it?
This is the only way I know how.
Oh, okay. There's no statistic. Right?
Correct. Yeah. So it's just looking at graphs. Okay.
got it.
So we have linearity, and then we have to do the residual plot for homoscedasticity. Yes? Yes. We feel that. And so what homoscedasticity, I don't know if anyone has another way to explain it, but what it's looking at is what is the discrepancy between values across here. So if it was met, this cluster of points would be consistent across, right? So it's not consistent because it's really high up here, and then it's low down there. So that's what we're looking at, and that's what that's telling us is that for different values of x, as we go across the magical plot, that the value, I don't know how to explain it.
They become more predictable.
They should. Like, they should be consistently predicted across the values, but because it's not consistent, that means that there's, like, wonky stuff going on, basically, in the data.
There accounts for differences in how they're plotted. Like
Yeah.
why are there differences or different variances?
Yeah, and so, yeah, does that make sense? It's really otherworldly and confusing to me, but that's how we do it. Any other questions on that? Okay, so, and if we can always talk more about it. So then the last one is independence of observation, so that's just in the design. Did they plan it well, that type of thing? We take it on faith, random selection, blah, 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 all that stuff. So there, if you see in the packet, so there's options when the assumption of normality is not met. So these are different ways that you can address problems with normality. I think that's something that we'll kind of skip over for right now, but we can definitely address again when we do kind of like non-parametric testing. So I think we'll go back to that. So just don't worry about it right now. Okay. So yeah, exactly. And like
No, I was just saying
prelim, like,
one of the things on the prelim is the non-parametric test that it suggests in the packet, like the Spearman's row and
yeah.
the Kendall style. It definitely asks about that.
Yeah. So I really want to like help you guys, obviously, with the prelim and stuff. So if we can get through like our curriculum, like just do it. Do what we gotta do. We can like study, all that. Okay. So we'll talk about the hypotheses a little bit. You've probably seen like the Pearson correlation coefficient R. That is the Greek symbol for it in the packet. And so it's determined as a value between -1 and 1. And so our null hypothesis is that that would equal 0, because that means that there's absolutely no association between the variables at all. Whereas For our alternative hypotheses, it's either the two-tailed, where it does not equal 0, or you can have a one-tailed, where you kind of predict the relationship between them. Does that make sense? Okay, let's run a correlation. So we're going to go to Analyze, Correlate, Bivariate, and then we're going to click over our variables. Let's forget about ethnicity for a second. Forget about it. Yeah. And so there's a lot of things that you can do here, but we don't need to click anything. Just make sure that Pearson's correlation coefficient is picked. And as you'll see, the non-parametric tests are options there. So for later. So you can go ahead and run it. And I like correlations because they're clean and easy. Like, look at this one table you have to look at. Like, that's so great. Just love it. So as you can see, we have the Pearson correlation coefficient and then a p-value and the n. So basically, as we can see, we have a significant result. And as the Pearson correlation, that's very high. So that's a really large effect. And so when reporting that, you're going to say, always address the null hypothesis, put it in actual terms. So we're talking about income and depression. So there's a positive correlation, and so that means that as income goes up, depression goes up, basically, is what it's saying. And then we're going to report the R and then the p-value.
Can you say it? Sorry.
Yeah. Yes. So you would say in the population, the result was significant. We can reject the null hypothesis and determine that Pearson's R does not equal 0. And that means that in the population, as income levels go up, depression levels go up as well. And you can say this is a large effect, or a large correlation, association, whatever word you want to use.
So R equals 0.846,
Mm-hmm.
and then P is less than 0.01.
Mm-hmm.
Okay.
So yeah. And if you have a significant result, we can do in the literature of our curriculum, often it says, like, what is the importance of this statistic? So because it was significant, we can look at the shared variance between the variables. And so by doing that, you can see, I really like in the packet, like how much of these two variables is shared with one another. And so by doing that, you just take the Pearson's R and square it, and so that'll give you the percentage. So whatever 0.8 times 0.8 is.
0.7157.
Yeah. So that's the amount of shared variance that these two variables have.
72%.
Yeah. So 36% of the variance in Y is associated with X, whatever you're looking at, basically. Yeah. Okay. Do you have any questions on that? Good. Oh yeah. So then, rho is the Greek symbol for that. So rho, when that's mentioned, that's what it's talking about. I forgot about that. So across like the stats life world, like they kind of translate R into the Greek symbol, so that would correspond with rho. Does that make sense? So like mean, like mu.
Okay.
Yeah, it's the same idea. Okay. So we can do the same thing separating out these groups. And so we use split file for that. There's also a bunch of other ways you can do it. So yeah, so like why don't we turn on split file really quick and just show you how to do that. So you go into data, split file, and then you can either do compare groups, organize output by groups, whatever you'd prefer. That's just what's gonna come out of the on the output. So I'm gonna do that, and then organize groups based on ethnicity. So not every I'll have to look at the homework and the PE, but I don't think all of the questions require you to separate them out, but I'll let you know. I'll look at those tonight. And so now that the split file is on, we can just run the same correlation again, and it'll separate them out. So bivariate, and there it's already there. So the split file kind of works as like an on-off button.
What are you doing with the split file versus what we were doing?
So the ethnicity portion of it, so all it's doing is separating out the groups. Whereas before we were looking at the group as a whole. So now we're going to look at like Chinese Americans, Japanese Americans, and Korean Americans, I believe.
Oh, got it. So it goes to the next level.
Mm-hmm. So you can do that, and it'll pop out the different ones. And as you can see, fascinating results. Only the Korean American correlation was significant. So that's why it's important to separate them out. Make sense? Cool. Let's move on. Okay. So we can go ahead and X out of that. We're going to talk about regression. Regression is super great. Love it. Super fun. I think, let me check real quick. Okay, so dataset 3 is what we'll be using. So now through linear regression, we still have just 2 variables that we're looking at, but instead we have an IV, which is predictor, and then a DV, which is a criterion. So all that's saying is that we're trying to predict scores on our DV or whatever variable we're looking at based on the characteristics of the IV. So that's really cool. We can do a lot of fun things with that. So if we wanted to predict depression scores based on one's income, taking that last thing that we did with the correlation, we would just do a regression for that. So it's important to have that distinction so you don't get confused. And all of the assumptions for linear regression is the same as the ones that we just did. So why don't we skip over that because we have a lot still. But we can address those pesky assumptions next week too. Okay, so for linear regression, we have the population beta now, and so that is also a number value basically, and that's telling us how, so that's just like a value that comes out, and it kind of also tells us the magnitude of the relationship that's going on, but it's not the same as correlation. It's determined a little bit differently. So it's basically the population beta is like a slope. If you remember rise over run slope, kind of telling you how much this relationship is. So maybe if it's really high, that means that the line would be really steep, but if it was really low, it'd be a little bit more moderate. And I'll write on the board in a second. But that's kind of what it's telling you. Okay, so for the example, we're looking at Researchers are interested in whether students' performance in college, as assessed by GPA, can predict their self-esteem. So the DV is self-esteem and the IV is GPA scores. So we're going to go to analyze regression and then linear. So we're going to put the DV in the dependent and then GPA or IV in independent variable. You don't have to add anything over here. If you so please, you can. Yeah. So we can run it. Okay, so it comes out with like a little bit more. Okay. So if we look at the model summary table, we have a bunch of R's going on here. We have R, R squared, adjusted R squared. So oh right, sorry. Okay, so this is the equivalent of a Pearson R correlation that we just did, right? So in the output, it's doing a correlation also for us, while it also does a regression later on. So this is just saying that's how much of the correlation is there, so that's still pretty large. And it was significant. But and if you'll remember, to get the shared variance, R squared, so it's just right there for you. And then adjusted R squared is accounting for error. So it's this equation that they've output, and it's kind of just adjusted to be a little bit more accurate to the population. And so when we report the results, we're going to report the R squared, the R squared adjusted, and the p-value. Yeah. And then, so when we get a p-value, we can, that is less than 0.05, that tells us that we can predict scores, like significantly predict scores in the DV based on the IV. So what that's saying is that, so we're looking at self-esteem as predicted by GPA scores. So if you have higher GPA, that can predict self-esteem scores, basically. What's another way to put that?
Wouldn't you want to look at it the opposite way though?
See, that's, yeah, it depends. And that's why the direction matters, because it changes the question a lot. And so in research, that's where you know, the fundamentals of theory and the behind the design is really important, because you can always argue stuff like that. Like, it could be opposite. Okay, so does that make sense to y'all? Cool. And so based on these results, we can also use the R squared to say that 40.6 of the variance in self-esteem is associated with GPA. So that's just using the correlation to kind of make determinations about the data that we have, right? Yeah. Okay. Any questions on that?
So for this data would be using the unstandardized coefficient?
I don't think we, yeah, I don't think we do that quite yet. So down here, we have our coefficients, and this is our beta, standardized coefficient beta. This will come into play later, and that becomes really important when we do multiple regression, which is when we have multiple IVs, right? So this will help us kind of determine what's going on with these different variables. variables, right? Okay, so there's
I would try to get up and help you, but I probably wouldn't make it.
So we have our regression line equations, super fun stuff. So basically, I think this will seem a little bit familiar because we're talking about non-standard versus standardized kind of distributions, or basically. So for the non-standardized equation, we can do this, bx plus a, right? So this is what we mean by prediction. So like we've seen this before, like y equals mx plus b, right? So all that, the a is the intercept where the x, yeah? When x equals 0 is where the y is. So that's just like the intercept. That's all, that doesn't really tell you a lot, basically. The b is that slope that we were talking about. So how intense is this prediction for y, basically. And then these are just the different values of y. So all we're doing is taking the data and putting it into an equation. Ooh, that's why we love math. And so that's what that's telling us. So versus the standardized regression equation, okay, so then this is taking our scores and standardizing them. So we're taking, let's say, like it would go like this. Like that would be our line for the non-standard. All that the standardized line is doing is like putting it through 0, 0. So it's making it standardizable to other distributions and that type of thing. Does that make sense? And so that's just the distinction between them. And so because of that, like the a would just be 0, so you don't include it. Okay, so this is also the slope of the standardized regression line. And so R, or Pearson's R correlation, that is just the beta in bivariate and linear regression. Does that make sense? So what it's all that's saying is that later on, we will be using different things, but because this is just bivariate or linear regression, we only have 2 variables that we're comparing. This R is our beta that we're using. And you can just use the R from the output, basically. Does that make sense? Mm-hmm. Cool. Yeah, and so that's kind of how you use it, and I think, yeah, in the homework, it'll ask you to just like use the data to write these equations. And so, let's look at how to do that. Okay. So, where would we find our beta on here? The beta, so we're gonna, so y equals mx plus a, what would it be our b? Actually, it would be, because this is the unstandardized. So this is standardized versus, or unstandardized versus standardized. Do you see what I mean? So it would be 9.4, and then this, the constant, that's just our intercept, right? So it would be y equals 9.4x plus 36.3. Whereas for the standardized, then we would use the beta over here. Does that make sense? And so this is just, like, I don't think that you'll use these equation lines very often in your practice as a clinician and a researcher, but it's important to know, like, that's what the data is doing, and that's what the graphs mean when we look at them and, like, all that.
So should we always use unstandardized coefficients? Like when would you use the standardized?
So, like on the homework, it'll ask you to just like write the equation of the unstandardized and standardized equation lines, and so that would be your determination.
So the homework
Hopefully, I mean, I'll take a look at them
I
before.
think this is what Dr. Mayer was talking on Thursday.
That's what, I knew I wrote it down
That
somewhere.
standardized it was within when you're trying to compare the same.
Yeah. Okay, so what standardization does is making it so like you have this research study that you're looking at, but if someone else like replicated it or did a different but similar study, you would be able to compare kind of the results. Whereas unstandardized, that's kind of like subjective to that study's own data, and like a different one, like you wouldn't be able to compare them because it'd be like off the charts kind of wonky. But by standardizing it, you're making the slope to go through zero, and so you can compare those lines between different studies.
So like which one would have like a steeper
Yeah.
versus like which one would have a flatter kind of
Yeah.
figure.
Cool. Questions?
What does the equation look like? You were saying that it would depend on the equation.
So if it's asking you for this unstandardized equation, like the words will match up. Do you know what I mean? So it'll like, what's the unstandardized equation? You would use unstandardized coefficients. But if it's asking for the standardized,
Oh, then you use the other.
That's, and it's in the, like, bivariate, or, like, multiple levels when we would use the standardized to compare between.
Earlier when we were talking about this, you were saying that R equals beta, but here, according to, the model
Yeah.
summary R is the same as the beta.
If you can, sorry.
Okay, got it.
They will be the same. So when we add more variables to the equation, we won't have a Pearson's R because correlations are only between two variables. Whereas when we add more to the equation, to our thing that's going on, like we'll have different betas for each one, and it won't correspond.
Okay.
You know, does that make sense? I'm really hot. Okay. Any questions?
I feel like it'll make more sense once we do the homework.
Yeah, and I will check out the homework and like let you know if there's any red flags, or like I've kind of tried to look at them and like change things that maybe weren't relevant to what we talked about and like that type of thing. So I'll do that and then I'll send it out. So the syllabus is kind of wonky, so I'm going to change it. But yeah, so it'll be due.
It's still a shadow on the
Right.
road, like that.
February 11th.
So okay, since it's Monday, if you could send it to me before, like if you want feedback for the homework, please send it to me by midnight on Friday, so I can have the weekend to like look it over and give it back to you by Monday. Otherwise, it'll just be due on Sunday at midnight. Does that make sense? So if you send it to me before Friday at midnight, I will give you feedback by the time we come back to class. But otherwise, just send it to me Sunday night.
So like this one you would want for feedback by the 8th.
Yes. Yeah. And let me know if you have any questions, and like I'm available. Like email me, text me if we want to talk about this stuff, because it gets really wonky.
I'm just gonna walk down the street and find where you live.
Yeah, come over. Yeah, it can be really frustrating because it's like, why does this matter? But I think it's important to understand when we're doing this data and like with our research and stuff to kind of understand why it works and why, because it's like seems very like mystical, like math, like why are we applying this to real life? But okay, I'll shut up.
I mean, I get the importance of it, just the subjectivity of it though kind of gets
Yeah.
to me.
Yeah.
Like, yeah, we're learning all this, but it's so subjective.
It is. And I think it comes down to the fact that, like, in reality, in the field, you can make your own decisions about things because nobody's like, that's wrong.
Right.
Like, there's no one person that is, like, there's no Bible that's like, this is how it is.
Right.
Because it's very different arguments.
But then that's why we can like break apart other people's research essentially.
Exactly. Yeah.
Yeah.